So the conductor is at the center. From here till the outer layer of insulation, how much resistance is offered by these insulating layers to the flow of current or to the leakage current? That I have to find. Clear? So let me erase this. Yeah. Now, did you understand what I'm doing? For that, what is the radius of this? This is radius of the conductor. Radius. Let me mark the radius of the conductor. That is small r. Small r is the radius of the conductor. Now, from here to here, from this center, from the center to last layer of the conductor, that radius, see, the small r is radius of the conductor, whereas capital R is the radius of the insulator, means still the outer layer I'm considering this as capital R. Okay, from there to here, capital R. Now, after this, from here, I should find how much resistance. You can see here, this leakage current, actually in this case is what happens, students. This is how considered single core cable. It is single core cable. Okay. In this kind of cables, what happens? The leakage current always flows radially outwards. See, radially outwards means from like this, it goes away from the conductors. It goes radially outwards. Can you see here? From the center towards the surface, outer surface. It goes like this. So the cross section of the path, of this current, this kind of current is not constant. It will be always changes with its length. Are you getting? It will not be constant. The cross section means the path of the current will not be constant. It will be varying. It will changes along with its length. So the resistance offered, the resistance offered, we have to find here how much resistance offered by this cable to the flow of to the path of leakage current. That I have to find. That is nothing but insulation resistance. How much resistance is offered to this current, to the flow of current, because I don't want current, but there will be some leakage of current. That current, if there is current through the insulator, then can you call that as an insulator? Insulator should not allow any current to flow through it. But there will be certain leakage current here, but still you have to, that's why you have to find how much how much resistance offered means how much it opposes. That insulating, whatever you have inserted here, no layers, how much resistance it will offer means how much resistivity, how much it opposes to the flow of current. That I have to find. Did you understand what I'm doing in this derivation? Just I wanted to find the insulation resistance of the cable. Why it is so important? Yes, it is very, very important because I know that, see here there is a conductor and there are so many layers of insulator. What is the purpose of inserting or winding this or having this insulating layers above the conductor? Because the current should not go out. It should not leak. Correct? No, the current should not, it should not allow the current, whatever is there, that should be there only in the conductor. It should not come out or it should not leak. Clear? But there will be still. That's why I have to find how much resistance is offered by this leakage current. How much resistance is offered by the insulator to the leakage current. Are you getting, students? Now let us start the derivation. First I have to understand what I have to do, then I have to proceed with the derivation. So now my purpose is to find the resistance, insulation resistance, because this is the property of that insulator, how much it can sustain, how much it can stop the flow of current through it, through that insulator. It should avoid the flow of current in the insulating layers. That's why how much resistance it will offer, or it depends on what are the factors, so that I will also come to know this. If I know in advance the resistance of the insulator, then I can design anything, any cable depending upon that parameters. Clear? So let us start with the derivation now. Okay, now first I have to consider in this path. No, I know one thing, the current always moves radially outwards. Radially outwards, like this it goes. Okay, radially outwards towards the surface of the conductor, towards the surface of the insulator. Like this it goes. So in this way, in this path, how will I find? There are so many layers of insulators. So let me consider a small elementary length. Okay, to start with, let me consider a small elementary length. That is what I will do is, I will consider a small distance dx. See, instead of writing here, I will write separately, students, so that you will understand. Here, see, there is a small conductor. Here above this, outwards, this is the outer layer of the insulator. Now, I will consider a small elementary like this. That distance, I will call it as dx. See, this distance, this is the dx. I will call this as dx. I will find out how much resistance is offered by this much of length. This is also a length of insulator. No, see, this is width of insulator. How much resistance is offered by this much of distance? Then to find the whole from here to here, if I integrate it, it's as good as finding it. Clear? So first I will find out how much resistance is offered by this much of distance dx to the leakage current, which is coming outwards like this, radially outward. Then to find the total resistance offered throughout this length, for this length, you know, you are very already you are very familiar that you know that if I integrate from where to where, from here to here, how much resistance is offered. So just integrate this from this distance to this distance, you will get the total resistance. Hope it's clear now. Okay. Are you there? Now let us start now derivation. So what I will do is, I have written here d is this, small r is radius of the conductor, d small d is capital, this is small d is diameter of the conductor, capital R is the, what is capital R? That is actually the radius of the cable. Capital R is the radius of the cable. This is very important. Conventions are important. Radius of the cable, because include complete cable is I've shown here, right? So this is radius of the cable. Radius of the cable. Then small r is already have told you, capital D will be diameter of the cable. Diameter of the cable. Diameter of the cable. So purpose is very simple. What I'm doing, I am finding the derivation. I'm finding the insulation resistance formula. That formula I'm deriving for insulation resistance. So to derive that insulation resistance, I have to follow the procedure. So let me consider an elementary distance dx. That is elementary section I will consider in this cable. That is, consider a small elementary distance dx. Okay, like this you consider a small elementary section and call that section as dx. The width is dx. So let me write here, this is dx. Okay, this is very important. Now how much from here to here? See, from this distance to this distance, let me call it as x. Can you see here? From this distance to this distance, I'm calling it as x. Why you have to call from here? If you are, see, this is conductor means from here to here dx is there. Okay, this is dx, distance dx. So from here to here, I'm calling it as x. I have written separately so that you can make out. Okay. See, from this distance to this distance, I'm calling it as, so I am considering the small section dx, which is having the distance x from the center. Clear? From the center of the conductor till the elementary section, the distance is how much? X. Why you are so bothered? Because I want this. Each and every parameter is important here. That's why. Okay, now let us start now. You know that as the leakage current flows radially outwards, as I said already, the length along which the current flows in an elementary ring is dx. Correct? No, this one dx. The length is dx. Now, in this case, cross-sectional area will be perpendicular to the flow of current, which purely depends on the length of the cable. That's why cross-section area becomes, are you getting? Cross-section area is equal to cross-section area. This is very important. Please understand. Surface area. When I complete the derivation, you may follow this students. Surface area for the length. Surface area for the length. Surface area for the length L. Why I'm writing completely? Because you should understand this. This is very, very important derivation. Definitely will get in exam. Most frequently asked question it is. That's why. Okay. Cross-section area is equal to surface area for the length L of the cable. Now, what is the surface area? Why did I write this? Can you just see here? The circumference is 2 pi x. Surface area for the length L of the cable, I will write 2 pi x. For the length L, that's why 2 pi x into L. This is actually the cross-sectional area for only that much distance dx. I'm talking about area for the length L of the cable becomes 2 pi x into L. The resistance of this elementary section will be equal to, since it is elementary section, that's why I'm using small d. Only for small dx distance, the insulation resistance will be given by dri is equal to rho L by A. Using that derivation, rho L by A, using this, what I have used the formula rho L by A. Okay. Using that formula, I will write, it becomes rho into Ls dx, because I have considered only small length, small elementary length dx, L by A. Area of that small length, what you consider dx, no, that for that dx, what is area? Area is nothing but 2 pi x into L. That's why I told you that 2 pi x into L. How it has become? Because cross-sectional area is perpendicular to the flow of current, which purely depends on length L of the cable. That's why 2 pi x into L, rho L by A formula we have substituted, and we got this. Clear? So here, after this, it is the insulation resistance for how much distance? For length L, for length dx, only for length dx. But I want actually the total insulation resistance for the whole cable. That will be given by Ri. Small dri means it's for small distance. For how much distance you have considered. But here Ri, which is nothing but, how will I find this? You integrate this. Which one? This one, small dri, whatever you have got. No, you integrate. From where to where shall I integrate this? From where to where you need. From R to capital R. That's why I have to write small r to capital R. From there to there, what is the total resistance of what? Of insulator. Clear? So substitute now. R, this becomes R to small r to capital R, rho into dx divided by 2 pi x into L. Then if I integrate this, you know that rho 2 pi L is constant. Take it outside. Rho 2 pi into L. Integrate only this dx by x. Dx by x. From where to where? From small r to capital R. Then I will get resistance of the insulation Ri is equal to rho by 2 pi L.
Rho by 2
Yeah, ln x.
pi
Ln,
ln r by r.
yeah, ln x. Let me write one more step clearly. I have not applied the limit so far. R into R. Then if I apply the limits, then I'll get Ri is equal to rho 2 pi into L ln capital R to small r. This is very, very important formula. This can also be written as, you can express this in terms of diameter. This is, see, here also R is there, here also R is there. This is very, very important. Ri means this side resistance. This is nothing but insulation resistance. Insulation resistance, resistance of the insulator. Where that insulator is there, here, these are the layers of insulator. That resistance, this actually speaks about. And what is this R? This is nothing but radius. See here, this R and this R. This is very important. Notations are important here. Here also R is there, there also R is there. So that is not resistance. Here it is radius of the cable. This small r is the radius of the conductor. This is Ri is resistance of the insulator. Like that, clear? So now the same thing in terms of radius, if I express like this, I will get. In terms of diameter also I can express. Then it becomes rho divided by 2 pi L ln d by d. Capital D divided by small d. Sometimes he will give in the problem, we will express in terms of diameter, then you use this formula. If he express in terms of radius, you use this formula, but both the formulas are correct. This is what the insulation resistance formula, where it depends on resistivity of the cable, 2 pi length of the cable, diameter, everything like this. This is the formula. Did you understand here? This is the important derivation, but very small derivation. It will be asked from 6 to 8 marks. You can go through the question paper. Many times he has asked this question. Derive for insulation resistance of the cable. And problems also will be there on this. So this is about, you have to use only these two formulas to find how do you calculate the insulation resistance, how do you calculate the thickness of the insulator, thickness of the cable, like that he will ask. So one problem I'll do, when I do that problem, you'll understand. Hope it is cleared now. Students, did you understand this?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, we will proceed now with the problems. Okay, I'll just clear all drawings. Next, let me take the problem. One problem I'll teach you how to do the problem. Yeah, copied on this. A single core cable has a conductor of diameter 1.2 centimeter and its insulation thickness is 1.6 centimeter. The specific resistance of the insulating material is 7.5 into 10 raised to, oh, value is there. Wait, just one sec. 10 raised to 8 it is. The value is 7.5 into 10 raised to 8. Let me change the color. It is 7.5 into 10 raised to 8 mega ohm centimeter. One problem you understand, later it will be very, very easy to solve. First of all, let us understand what he has asked and how to proceed. He has given certain parameter. A single core cable has a conductor of diameter D. So let me write D is equal to 1.2 centimeter. D is equal to 1.2 centimeters. Okay. And its insulation thickness is 1.6 centimeter. Insulation thickness. So T is equal to 1.6 centimeters. 1.6 centimeters. Next, the specific resistance of the insulating material means a rho. He has given a rho, resistivity. Specific resistance means its resistivity of that insulating material is 7.5 into 10 raised to 8. 7.5 into 10 raised to 8 mega ohm centimeter. Okay, let me tell you this. After this, calculate the insulation resistance per kilometer of a cable. He is asking you to calculate now insulation resistance per kilometer of the cable. So put question mark there. So next, if now this resistance is to be increased by 20%, then calculate the thickness of additional layer. Next we have to, if it is some condition is given, if that is satisfied, then you find the thickness of the additional layer of the insulation layer required. To proceed with this second parameter, so let us come to the first parameter, or we'll go step by step. How to find? We know that resistance of the insulation is given by the direct formula. Ri is equal to, I will write on the formula, Ri is equal to rho divided by 2 pi L. Either you express in terms of radius or you will express in terms of diameter. It's left to you. Ln R by R. Let me write down the formula. Then I will think about how to solve and how whether which is unknown and which is known. Let me decide later. Rho would by 2 pi ln R by R means which is known and which is not known. Rho is given. Length. Let us see here. Calculate the insulation resistance per kilometer of a cable means length is given for per kilometer means 1 kilometer. That is 1 kilometer means it is 1000 meters. So that is also given. Even this is given. Are you getting, students? Rho is given. Per kilometer he has asked. So per kilometer means length is also given. And radius is not given, but I can convert. Diameter is given, I can convert in terms of radius. I can express that in terms of radius. We will see that now. Okay. Capital R means what? We'll see that now. That is diameter. This is radius of the cable. This is radius of the conductor. This is very, very carefully how to substitute. Now, let us see. D is equal to 1.2 centimeter. So let me find out one by one parameter. I'll keep ready one by one, easy. For my calculation, how I want, like that I will keep ready. Now I want this. I want to express this in terms of radius. So R is equal to D by 2. R is equal to D by 2. Now what is diameter? 1.2. 1.2 divided by 2 is equal to 0.6 centimeter, I think. 0.6 centimeter. Yeah, this smaller is diameter of the conductor. That's why using that. Now capital R. So when one capital R is, what is capital R, students? So this is over. Now